speaker for today is Professor Carlos J. Santamarina. He is a professor and the co-chair at Georgia Tech. He earned his bachelor's degree from the Universidad Nacional de Córdoba and completed graduate studies at the University of Maryland and Purdue University. He has taught at NYU Poly, the University of Waterloo, KAUST, and Georgia Tech. His research team combines experimental and numerical methods to explore geomaterials, sediments, fractured rocks, and complex fluids, with applications across energy geotechniques in coastal offshore environments, ranging from resource recovery to energy and waste geostorage. A frequent invited speaker, Professor Santamarina delivered the 58th Tergazzi Lecture on Energy Geotechnology and is a member of both the Argentine National Academics. Professor Santamarina has received numerous honors, including ASTM's Hogen Togler Award, the Korean Geotechnical Society Award, and Saudi Arabia's Tarek Al Kasabi Award. Thank you so much, Professor Santamarina, for joining us here. The stage is all yours now. You may start. Professor, you are on mute.
Yes, I'm trying to share my presentation. Let me proceed. And now you should be able to see my slides.
Yes,
Please
perfect.
confirm. Excellent.
Perfect.
And while I clean up all the other controllers. Excellent. Well, colleagues, it is a pleasure being here with you today, and thank you so much to the organizers for inviting me to participate in this wonderful series. Today, I would like to look at the energy situation in the world, and I'm going to do it from an Earth perspective. I work in the subsurface, so from a geo component of the energy sector, and I would like to plant the seeds that there are beautiful and fascinating physical-chemical processes that control our energy situation. So with that in mind, let me start by taking a brief look at the energy situation worldwide. Why are we so concerned about energy? Well, because it is critical to the quality of life. For example, the availability of water, life expectancy, infant mortality rate, schooling, education, access to electrification are all intimately related to the amount of energy or to the power consumption. Just to put a few trackers here, where it says 0.1 kilowatt person, 0.1 kilowatt is the rate of a healthy diet. This is like a 100-watt light bulb. This is our lives. And the rate of power consumption by our bodies. So notice that each point here represents a different country around the world. Notice that there are many countries where the average power consumption is lower than a light bulb, lower than needed to sustain our lives. Therefore, indeed, the quality of life in those countries is pretty bad, with high infant mortality rate and very low life expectancy. On the other hand, we have countries that are consuming above what is actually needed, because quality of life basically saturates by the time you exceed 5 or 6 kilowatts per person. And this is the most consuming countries, as you can imagine. So the key here is to be above 1. It would be nice to be above 3 or 4. Most European countries are in this region between 4 and 6 and 7. And the yellow dots, because of India hosting this event, I'm showing India where the yellow dot is. So India is at about 0.5 kilowatt per person, and it is on a critical path to increase that availability to power in order to increase all other aspects of quality of life. And that is what all countries are struggling. So if I plot quality of life versus power consumption, and I've done this for the last 40 years or so, you see that all countries are moving along this line. In other words, they are increasing power quality of life, but at the expense of increasing power consumption. And this is unsustainable. So in order to develop a sustainable energy system, we have to figure out how to reduce power consumption in the more consuming countries, including the US, of course, and how to improve quality of life without increasing power consumption in countries under development. Now, the predictions are pretty rough, and there will be a 25% increase in energy demand in just the next 15 years. So this would require, let's say, 5,000 of the largest nuclear power plants. So this is impossible. This is not going to happen, which gives us the idea that the system is quite under stress. Now, the other bad news here is that 80% of all our power consumption comes from fossil fuels. And while the component of the renewables is increasing relative to the whole power consumption, the fact is that we are going to increase consumption of fossil fuels in the foreseeable future, at least for the next 20 or 30 years, in part because to transition out of fossil fuels requires a large amount of energy for the new infrastructure. And because all that energy is coming from fossil fuels, the transition out of fossil fuels will be fueled by fossil fuels. So power consumption is going to increase, fossil fuel consumption is going to increase, and that brings us to a real problem that, as you all know, that we start with hydrocarbons, we add the oxygen, we end up with CO2, and in fact, this is a nice rule to keep in mind. For every kilogram of fossil fuels that we burn, we release 3 kilograms of CO2 into the atmosphere. This is the heavy molar mass of oxygen coming into play. And so where is all that going? All that is going to the very thin shell, thinner than this white line, that is the atmosphere, is about 10 kilometers thick. And all that CO2 is accumulating in the atmosphere, and the atmosphere is the one that creates the thermal balance between the Earth, on the surface of the Earth, based on the solar radiation, and is trapping that radiation, and temperature is increasing, and the rest of the story you know. But as the IPCC predicts, there will be increased frequency and intensity of extremes, and the natural carbon sinks onshore and offshore are going to become gradually less effective. So the news is not good. 2050 will be quite a challenging decade. Now, I would like to say some good news here. Well, one of the compounded effects is that population keeps increasing, and then there is big concern about population growth. But there are good news there. Basically, all around the world, probably except for Africa, but Africa is going down very fast. The number of children per woman is decreasing, and is already, in most countries around the world, is already below 2.1, which is the number required to maintain the population. So eventually, now there is an inertia in the growth cycle of the population, but eventually by the end of the century, the population will be finally decreasing, but we will be at about 11 billion, and with a fairly old population, by the way. India is right there on the transition. Right now, it's somewhere between 2 and 2.2, depending on what parts of India we are talking about. Now, the other good news is that if you compute, and we've done it starting with, if you compute the moles of carbon needed to produce 1 kilowatt hour of energy, and we've done it starting with wood, and then into coal, and then into petroleum, and into methane. So we know the energy mix throughout history, and we know how long the hydrocarbon molecules were, so we can compute how much CO2 we were emitting. So we see that we started at about 10 moles of carbon per kilowatt hour, mole. So these are Avogadro's numbers. So it's a big number. And now we're at about 5.2. And the idea is that if we get to a hydrogen economy, so burning hydrogen releases water, there are no more CO2 emissions. And so if it was pure hydrogen obtained in a way that it doesn't release CO2, that we are going to question in a few minutes, then we would be at this point. Now, how are we going to get from the 5 moles of carbon per kilowatt hour to this zero? Is unlikely to be in the near future. Renewables should help us in some of the transition, but we are clearly in a carbon economy. It's not clear how we're going to get out of it in the foreseeable future. Now, the other good news is that trees are amazing. They are the best carbon capture techniques that we have. And it takes, if you compute the amount of CO2 that we release, it would take about 10 trillion trees, a trillion trees to help compensate for some of that. The US has committed to 1 billion, so a thousandth of that, even though the US produces about 20% of all the CO2 that is emitted in the world. And it's not that it's lack of a space. That would require about 0.3% of the available farmland in the US. So clearly countries like the US can and must do much better than that. There are a whole series of details that we can go into the importance of trees, but I really bet on the importance of trees. So let's give them a good chance. Now, before I leave this series of introductory slides, I would like to bring some clear relationships to help us our analysis. And if you divide the size of the economy with the amount of energy that we consume, with the amount of CO2 that we produce, these are all teradollars, terakilowatt hours, terakilograms of CO2. So we divide by tera and by 110, we conclude that $1 that goes into the economy is directly related somewhere in the economy to the consumption of 1.6 kilowatt hours and the release of 340 grams of CO2. For every dollar we spend, we release, or let's say for every $3 we spend, we release 1 kilogram of CO2. This is such a robust relationship that I think that is central for us to analyze any complex situations. And somebody coming with the idea of circular carbon economy or net zero by 2050, please give it a try, and you will see that all those are utopic concepts. The other thing is that given the fact that we are going to depend on fossil fuels for the foreseeable future, and the petroleum companies know it very well, they are in the process of investing several $1 trillion to increase production, then it is critical that we do carbon capture and storage. And that just the capturing part will cost about $2 trillion per year. Now, it sounds like a lot of money, but let me tell you that is the size of the military budget worldwide. That means that we have the resources and we have a choice to make. And so now, with that picture in mind, with the good news and the bad news, then let's go and look at what are the current resources. And I'm going to present each of the energy resources that we use today. And for each of them, I'm going to show you an example of physical chemical processes, which actually doesn't apply only for that resource. It applies across the border, but I'm going to use them as examples. So let's start by what are the energy resources. We use the fossil fuels, oil, gas, and coal. We would like to use more renewables, geothermal, hydroelectric, wind, and solar. Hydroelectric is pretty much saturated worldwide, so it has reached where it can reach, and that's it. Then we're talking a lot about hydrogen these days. And nuclear, we would like not to consider it, but it's there and probably increasing part of the mix. Now, there is another component that we need to realize, that in order to go through the transition, we will need lots of minerals, the copper, the rare earth minerals, etc. And in fact, this is the bottleneck. the availability of minerals. And in all this, we can also add the possibility that there is a good contributions by conserving energy, number one, and being more efficient, number two. So let's start with oil. And uh, oil, there is plenty of resources. Right now, we estimate approximately 50 years of resources, but the minister in Saudi Arabia said that already 50 years ago, the Stone Age didn't finish because we ran out of stone. So the fossil fuel era will not finish because we ran out of fossil fuels. I think that we're going to finish the fossil fuel era because we need to get out of fossil fuels. Now, so the critical component of recovering oil is how oil interacts with the medium and capillary forces. And capillarity is controlled by two effects, surface tension and the contact angle. And so what are the surface tensions for water in air with its own vapor? It's about 72 millinewtons per meter. As soon as we have oil and water, for example, it drops to 35. We'll come back to this concept because we're going to talk about CO2 later on. Now, at the interface, particles may accumulate, small particles. And so in this case, I'm accumulating nanoparticles. And so this is a water in oil droplet, a water droplet in oil. And you see that as I began contracting, it didn't contract nicely as a Laplacian surface. It buckled like a shell. This is because it got coated with nanoparticles that we cannot see at this point. It got coated, and as it contracted, it formed a shell, and then the shell had to buckle. This will have huge implications on the possibility of recovering that oil. So if you follow this literature, you will see some possibilities on the use of nanoparticles. Now, what about the contact angle? Well, if you put a droplet on the surface and you tilt the substrate, you will see that it tends to curve as shown. That means that the advancing, you're moving against the edge here, the advancing phase has a higher contact angle than the receding phase. And why is that? Because, well, that the interfacial tension between the two fluids is also getting stuck on the edge. There is an adhesion force. That means that the contact line develops some adhesion, and that's critical from force equilibrium, going back to Young's equation. And you can add that force and convince yourselves that there is a hysteresis between the advancing and the receding contact angle. It is not always easy to measure, but here it is. We are inflating a droplet. As you can see, it's advancing. And so we can measure this angle. And this is the advancing contact angle. It's quite steep. And now we're going to suck it in. This is the needle. It's going to pull it back. And as it pulls it back, the contact line is pinned, and it doesn't want to recede so much until it's, well, they flipped again to the beginning, until it gets to an asymptotic value. That is the receding angle. When we just put a droplet on a substrate, we don't know where we are. It could be somewhere between advancing and receding. So it's good to do this injection and pull out fluids to actually see the true hysteresis. Between the two, we control capillarity. Now, if I change the surface tension with surfactants, the behavior can become quite different. This rod has no surfactant, no detergent. This rod has a little bit of soap at the end. As soon as we touch it, the surface tension breaks down, and the rest with high surface tension pulls it to the edges. You can see that happening every time we wash the dishes in our homes. And that will have huge implications to our ability to recover oil. But when we recover oil, the water-oil interface goes through the pore constrictions in the porous medium of a rock, and there is a self-regulating mechanism where the surfactants get closer and then further away and closer and further away, which is identical to what happens inside our lungs, and these are called pulmonary surfactants. So this adds a little bit complication on our analysis of how much oil we can recover, and some related processes. Let me jump into gas, and I am beginning to keep track of time here. Gas reserves are quite strong, quite important. The revolution happens with gas in shales. Shales have very small pores, nanoscale pores. Clay particles are so compacted that the pores between them are very small, but gas is absorbed and filling the pores. And the revolution in gas that took place is because of going in and breaking that whole structure, which is called fracking, and then being able to pull that gas of the nanopores. There is high energy density in gas, similar to oil, but I'm going to talk about the case of hydrates, and I'm going to explain what they are. By the way, the gas revolution was so incredible that look, in just 6 years, this is the southern part of Texas. At the beginning, there were a few wells, and very rapidly, there were 18, 20,000 wells within 5 years. Now there are 25,000 wells in this area producing shale gas, depleting faster than they had originally anticipated. Now let me talk about methane hydrates, because it's a wonderful physical phenomenon. This is the ice that then you can light it with a match, and as the ice melts, methane gets released and it can sustain a flame. And so this is actually methane molecules in water and molecular dynamic simulations. And you will see very soon that cages begin to form, trapping a methane molecule inside the cage. These are clathrates, and this is what is called methane hydrates. Now, methane hydrates have a stability field. In other words, you need to be under low temperature, let's say 2 degrees, 4 degrees Celsius, and high pressure, let's say 1,000 meters of water, 10 megapascals. And so there is a region for the formation of methane hydrates. And in this case, I have assumed that the water depth is 1,500 meters. And so all this region in the blue area is where hydrates can form. Now, hydrates float. So if methane comes out, it forms hydrate in the water column, but the hydrate mass will float and then dissociate. So you never see it at the surface. But if it forms in the subsurface, then it will get stuck inside the sediment layer. And these are called hydrate-bearing sediments. Now, when this ice forms, it's like ice. When it forms, you can do this experiment in the refrigerator. If you have clay and you saturate it with water and you freeze, it forms ice lenses. Why? Because there is a crystal pressure in the ice formation. You can compute from Laplace surface tension. It creates a force, and if that force is sufficiently high, it will push particles, the sediment particles out, and segregate, forming lenses. This is from India, the Krishna Godavari basin, which is northeastern part of India, a very rich oil and gas field. And we recovered the cores, and you see all these, we made the soil transparent, this tomographic image, we made the soil transparent, and all these other lenses that you see is actually segregated methane hydrates. And so in some places you can find it filling the pores in sands, and in some places moving the particles apart, forming ice lenses. And in fact, in most parts of the world, wherever you see a blue dot, it is in the form of segregated ice lenses in fine-grained sediments, including in the Krishna Godavari basin. Now, this is very difficult to recover. A gas will migrate towards a well, oil will migrate towards a well. Methane hydrates are solids, and you depressurize and it migrates toward the well, but that depressurization decays rapidly, and then you don't dissociate it anymore. So it's very difficult to produce, particularly when it is segregated. Now, there are incredible possibilities. For example, if you look at the enthalpies of the formation and dissociation, if you have methane hydrates and now you're surrounded with CO2, the methane hydrates will open up, the cage will open up, release the methane, and take a CO2 molecule and form CO2 hydrates. And so that would be amazing because we recovered a fossil fuel, but we buried the CO2. And in fact, it does work. And this is monitoring with P wave velocity on this hydrate replacement, methane CO2 replacement. Difficult, but the opportunity is interesting. Now, India works, and India and most part of the world depend still on coal, particularly India, I have to say. There is plenty of it in Australia as well. And the energy density is not so high because you have other components, but so it's half of gas and half of oil. But there is plenty of coal. So the question is, what can we do? Just to have an idea, if you go back to the composition, you will convince yourselves that 1 ton of coal releases 2.5 tons of CO2. Once again, we go back to the relationship we said before, and produces 80 kilograms of fly ash. And this is a tricky one because it needs to be stored somewhere or used. And it has led to very historical failures of these ponds filled with fly ash. All of a sudden they break and they release the fly ash, which creates environmental disasters. Now, take a look at fly ash. There are these cenospheres, like Christmas tree balls, and very thin shells, with some of them further inside. You have to wonder how does nature make it. So during the coal combustion, these droplets do not combust, and so eventually they come out and they solidify with plenty of CO2 in solution, and so they become these cenospheres. But they tend to be quite spherical, and that gives them very unique properties for this material. Now, one of the issues is that the cenospheres, or fly ash, when you mix it with water, gradually develops cementation. We are measuring here with shear wave velocity, and you see that within a few days, the shear wave velocity has increased, the travel time decreases, that means the shear wave velocity increases. That means that it gets lightly cemented. You touch it, you cannot feel it, but it is lightly cemented, and it locks in high porosity, which makes these ponds very brittle, very sensitive. The chemical processes are still up there to be properly understood. Now, so far we have done fossil fuels, and the key here is we are going to continue using fossil fuels for the foreseeable future, as I said earlier. Now the key is we have to capture and store it. And we don't need to store it for a very long time, probably 200 years, 500 years, because eventually, after an energy transition out of fossil fuels, then nature can handle the capture and storage. It has been doing it for the last 2 billion years or 1 billion years. So we don't even need 10,000 years. Probably, I think 1,000 years will be plentiful. But how do we do it? Well, we can inject it in places where there are coal beds that cannot be mined, or we can mineralize in mafic rocks, volcanic rocks. We can keep it as supercritical CO2 in deep saline aquifers, or use for enhanced oil recovery. Now, there are lots of physical chemical processes that take place in this, and we cannot underestimate any of them. I will explore with you some of them. So in order to hold the gas or supercritical CO2 beneath the surface, there has to be a seal layer, like a upper part of a balloon, let's say, so these fluids cannot escape. And the trapping mechanism is capillarity. So we go back to capillary concepts, surface tension and contact angle. And so we can look at the droplet here sitting on a calcite substrate through this pressure vessel and see what happens with the droplet as we increase the gas pressure. You see that the surface tension and the contact angle are changing. And so we may begin with this water droplet, it's surrounded by CO2 at 72 millinewtons per meter, but as it gets pressurized, it goes down to 30 millinewtons per meter. So the capillary trapping changes, but there is something else that happens. The water acidifies, and acid water takes the minerals out of their equilibrium and begins doing dissociation. Now, now imagine what is going on. We have the fluids that are moving, advection regime. We have diffusion taking place within the fluids across the channels and into the matrix. And we have reaction taking place of this acidified water with the minerals. And so we can analyze these three processes using Peclet number, diffusion and advection, and using the Darholer number, which is reactivity and advection. And so if the reaction is very fast and the seepage is very slow, most of the dissolution takes place at the entry point. But if the reaction is very slow and advection is very fast, we carry reactants all the way through, and the dissolution process has a different pattern, a different pore habit. Now, dissolution, wherever there is dissolution, the channel opens up. If it opens up, there is more fluid flow. If there is more fluid flow, there is more dissolution. So dissolution gives you a positive feedback mechanism that leads to flow localization, which is a tricky one. So now let's take a look at the core. It's a basalt, it's a mafic one. We're looking at precipitation here. Let's take a core, we put in a micro CT surrounded by water and CO2. So there is the core can represent the block in the matrix, and the surroundings are the fractures. And as you can see, is as time passes by, we can monitor the mass inside the core. There is gradual dissolution, and eventually precipitation begins to take over. So beginning with dissolution and then precipitation takes over, you see what is happening with the porosity. At the beginning, the porosity increases and eventually decreases. And then you can see the crystals of aragonite, this calcium carbonate, from the calcium that was in the silica. Now it is trapping the CO2, forming calcium carbonates. So this is mineralization. Now, we said that we want to move into a hydrogen economy. There is a lot of hype in this field around the world. Now, somehow we have gotten used to the fact that hydrogen has different colors. There is a whole rainbow of hydrogen. If nature is producing it somehow by itself, probably 4,000 or 5,000 meters at depth, by the process of serpentinization and producing hydrogen, that is totally natural, and that is white hydrogen. It costs nothing to produce it. Of course, it's not easy to extract it. We have to drill that deep. So the extraction may have some carbon release in the process, but the production does not. And then we begin saying, well, we may produce it by hydrolysis of water using solar and wind. Now, this is green, and then the story gets darker and darker because we may end up using fossil fuels to produce the hydrogen. So we don't know how much hydrogen nature is producing and whether it does it continuously. There are some individuals that are highly optimistic. I think that the jury is out there. In the meantime, it's worth doing the research. One of the problems with hydrogen is that, by the way, it has an amazing energy density. Remember, methane, this number was 46, oil is 46. For hydrogen is 120. It has a huge gravimetric energy density per kilogram. The problem is to get hydrogen to compress so 1 kilogram occupies a decent volume. Is very difficult. The molecules don't really want to come close to each other, so the density is very low. So you need very high pressure vessels, and then there is embrittlement of steel. So we have to be very careful with the durability of these pressure vessels so they don't become a bomb. And so it's not obvious. And so we may want to bring hydrogen molecules together, like for example, with nitrogen forming ammonia. So we have plenty of hydrogen, and so we have a higher energy density, and we have a carrier to transport the hydrogen. Now, there are other issues with solubilities, with viscosities, with fugacity, etc. Now, one way to store it is also to let it absorb onto mineral surfaces, because next to the mineral surface, it forms these monolayers of high density. In fact, the density is several times higher than the density of the gas itself in the bulk phase. And that is great if your mineral substrate has very high specific surface, because the mineral itself occupies volume. So you have some benefits next to it, but if the mineral occupies a large volume, you overall lose in the process. And so there is a trade-off. And summary, you need minerals with a specific surface greater than 400, 600 meters squared per gram. That means that you're talking about montmorillonites and activated carbon. Now, what about nuclear? Well, nuclear is fusion and fission. There are some hopeful signs that that may happen, but right now we count only on fusion, and the problem with fusion is the waste, the nuclear waste. And we have built basically 500 nuclear power plants in the history of nuclear energy since the 60s for civil purposes. And we don't have not one operating nuclear waste repository. And the Finland's repository keeps being postponed, but hopefully this year, next year, it will start in operation. But that's a problem. All the nuclear waste is still in tanks, like in pools, being stored with huge potential consequences, some of them which we're already observing. So the key here is to store it under great depth, so it doesn't ever appear into the atmosphere. We want to guarantee 100,000 years. Folks, we really the history, we can go back probably 10,000 years. We have to predict something 100,000 years. This is very, very difficult task to engineer for such a condition. And one of the problems is diffusion. So what is the diffusion of nuclei coming out of this? What will be the rates, etc.? So we need to look at diffusion with new eyes very carefully. Here you have two bentonite mixtures, one on the right-hand side that has been added potassium chloride, the other one on the right-hand side washed and with deionized water, and then you bring them together, you leave them there for a couple of days, then you pull it apart, you begin shaving millimeters, a tenth of a millimeters at a time, and measuring the ionic concentration. And now we can see the diffusion of potassium chloride from the right from the left onto the right. Now the story is not that simple, and depending on what is the companion ion, the diffusion, the effective diffusion of one ion is conditioned by the other one, because it cannot violate electron neutrality, or it creates an electric field that adds an electric drag to the diffusion process. And so let's start by saying that you're going to satisfy electron neutrality. So the fast one is going to be slowed down by the slow one, and the slow one is going to be speeded up by the fast one. So they migrate, the random walk evolves together. Now, what happens if the medium has ions to begin with? For example, a clay has the counter-ion cloud, the Debye-Huckel length of the counter-ion cloud, that those counter-ions also interact with the diffusing ions, making the story more complex. So diffusion requires new insights, a new understanding for the nuclear problem and for all problems that we have from biomedical engineering as well. Now, furthermore, in this storage, deep reservoirs, 500, 600 meters deep, for 100,000 years, we have long time scales and long spatial scales. All our laboratory tests are very small, so how can we simulate them? We can put them in a centrifuge, and actually we can see the effect of drift on ion migration. And the effect becomes quite measurable. Of course, we had to go to 7,000 Gs, but now you can see the drift of ion migration, and now we can compare gravity-driven drift with diffusion, and you see that gravity does bias diffusion. We cannot assume, like we always do, that diffusion is gravity independent. In fact, it does bias, and significantly. And it's not the Einstein the mobility, the random walk, or what you can measure in an electric field, because in these cases there are collisions. In this case, cations go to the left, anions go to the right. In this case, both are driven by the gravity in the same direction, which reduces significantly any electrostatic effects and friction. So don't underestimate gravitational effects on ion transport in large scale problems and long time scales. Geothermal, I can tell you what the beauty of geothermal is. Somewhere here, here it is. Oops. 98% of the Earth is hotter than 1,000 degrees Celsius. That's amazing. We have huge amount of geothermal energy, but we need to get down there and we need to be able to extract it. And so that is a huge potential. So now to extract it, this is what we're going to do. We're going to drill a hole, create a fracture, if there is not one readily available there, inject water from one end, pull water or steam from the other end. In order to make this Rankine cycle efficient, you want to do it in very high temperature, and they're going to be at high pressure. And as the water goes in, it gets hot. As it gets hot, it increases its thermal activity and the potential to dissolve the host rock. So there will be dissolution near the entry point, and then it begins carrying these ions. It gets saturated with these ions, but before it exits, it may go through phase transformation and drop these in some form of salts. And so there will be channeling at the entrance, and there will be clogging towards the exit, either within the fracture or in the riser pipe. Lots of complications in order to operate these systems properly. Finally, we need to store and we need to store CO2, we need to store hydrogen, we need storages in large quantities, and that means that we will need to use the subsurface for storage. And for different systems, there are different energy densities that we can attain. But let's go back to CO2 storage, and I will highlight a couple more issues here. Remember that it will be trapped by capillarity, so the seal has to remain, the capillary, the pores have to be small, and there will be this buoyancy that is pushing against the capillary trapping, and then CO2 dissolves in water and begins creating these convective currents. These are tears of heavy water with dissolved CO2 falling down. This is where the pH indicator, so you can see where the acidic water is. And so what are some of the consequences of acidification and trapping? Well, one of them is that shales are basically a high composition of clay minerals. These are phyllosilicates, which are gibbsite and silica tetrahedra, with different phases, and they will interact different with pH. So the surface charge changes with pH, protonation, deprotonation, and then the van der Waals and double layer repulsion are also going to changing the fabric. So as we acidify a formation, we're going to have strains because the fabric wants to change. So long-term stability becomes an issue. And so we want to seal the formation and we want to seal fractures. Like if you have the tire of a car and you want to seal a puncture. And so we are exploring different opportunities because it has to be with very low viscosity fluids, because we're looking at very thin leakage points, but still leakage points that will hinder the storage capacity. For example, imagine that you inject calcium chloride and then in another cycle, sodium sulfate, this 4 is moved. And so eventually when they two mix in the fracture, you're going to begin precipitating uh, calcium, sodium chloride. No, exactly, sodium chloride. And so, or calcium sulfate. So as you precipitate calcium sulfate, you begin to see here the needle shape of the precipitates, and you gradually seal fractures. Sealing fractures and preconditioning reservoirs is critical towards the energy future. And I'm going to conclude here by saying that the mining remains the bottleneck for the energy transition. Let me give you an idea. We need so much copper to upgrade the grid and to create the grid where it doesn't exist that we will have to open every year a mine of the size of the largest mine in the world in Chile. Is called Escondida. We have to open one of those per year and put it in full operation in a year, and it takes more than 20 years to open those mines if we find them. And so we are really in trouble. And if you've been following international politics these days, rare earth elements are critical, and this is 100% controlled by China. And so there are lots of issues in mining. And then what do we do with the mining products? The same way that we saw the fly ash collapse, we see mine tailings collapsing. Several examples happening in India in the last decade. And this one happened in Brazil, and it's catastrophic. It was perfectly stable, etc. And all of a sudden, it burst. Why? It was decommissioned. It had been stable for years. What are the undergoing physical chemical processes that lead to this situation? How can we prevent it? To conclude, I hope I have persuaded you that the energy challenge is a Terra-sized challenge. And we really have to look for massive solutions. If you get lost in the analysis, go for very simple relationships. This is a compass for the analysis. Be careful with fake technologies and false promises. I think that we have different strategies for the developed nations and the developing nations. We'll need to stop reducing overconsumption, and we need to jump into leapfrog technology so we don't do the same things that the overconsumption nations have done. Let's avoid following the same bad path. And I clearly, right now, we are not lacking science and technology. It's leadership that is critical. I hope you have seen throughout this presentation that there is a beautiful set of physical chemical processes, but they are quite complex and they are coupled, and so we need to understand them in depth. I invite you all to join efforts to be part of the solution. This is possible through to an amazing group throughout the last couple of decades, but above all, I want to say thank you once again to the organizers and to all of you for being here today. Thank you.
Thanks a lot, Professor Carlos, for the very insightful lecture.